Our lesson for today will be looking at Chemistry 1501. The topic for today is electron configuration. We'll be looking at lesson 101. Let us start. By the way, this lesson video is based on the electron configuration of ions, and we will be looking at other concepts like isoelectronic, and then we'll also be looking at the noble gas electronic configuration of the ions. But before we get there, I would like us to review the basics of chemistry a bit. I know that we already have lesson videos based on the basics of chemistry, but just to make sure that we understand, let us review, because we are going to need those basics. Now we know that we have a periodic table. On top of periodic table we have different types of atoms with different types of properties. We do have atomic masses, we have atomic numbers, we have number of electrons, we have number of protons, number of neutrons. So let's say, for example, we have oxygen. We know that oxygen is element number 8. This simply means that we have 8 protons. Simply means that we have 8 protons and 8 electrons. You can see that the sum of these will give us 0. That is why we don't have any plus minus on oxygen atom. Again, we have magnesium. It's one of the examples. It's element number 12. This simply means that we have 12 protons, positive particles, 12 electrons, which are negative particles. So with this information, we can know how to generate O2 minus. How come we have this charge? How did we get to this point? Now you should know that from the original atom, it simply means that for the element or the substance to become negatively charged, it simply means that it has more negatives compared to the positives. And then this number, this formal charge, actually tells us how many excess electrons we have, how many excess negative particles we have. And you should also know that we cannot tamper with this. The positive charges, they are located within the nucleus of the atomic structure or the central. They cannot be added or removed. The positives cannot be added or removed. So in order for us to get here, we did not remove the particles. We did not remove the positive particles, because we know that if we have 6 positive charges and 8 negative charges, the sum of this will give us this. But you should know that this is not what actually transpired, because we cannot tamper with the positive particles. So what happened is that instead of tampering with this, let us add more electrons, meaning that in order for us to get here, we have 8 positive charges and then we have 10 negative charges. It simply means that from here we've added 2 electrons to have this. Same goes to magnesium ion. It's 2 plus. So what actually happened? Remember, we cannot tamper with this. This will remain 12. So it simply means that we have removed 2 electrons. Removing 2 electrons, it means that we are going to have 12 protons and 10 electrons. taking the sum of this, it will give you this charge. So we call these our ions. With that information, we will be able to find the electron configuration. Let us try to write down the electron configuration of oxygen. Before we do that, let us write down this template in order for us to know the orientation. It will actually assist us on how to write the correct electron configuration. So let us write down the electron configuration of oxygen. Oxygen is element number 8, so it simply means that we are going to have our first electron configuration, which is 1s2, then we go to 2s2, and then we go to our p orbital, which will be 2p, so this is the electron configuration of oxygen. You can see when you add these exponents, it will give us the atomic number. Now, before we can look at the electron configuration of oxygen ion, I want us to start with the electron configuration of this. The electron configuration of sodium, it's element number 11. So you're going to start with 1s2, 2s2, 2p6, 3s1. So when we count, we can see we have 11 electrons. Now, how can we write the electron configuration of sodium ion? Now, the first thing that you have to check, it has a positive charge, so it means that we have removed electrons. How many electrons have been removed? Now you can clearly see by looking at this formal charge, we removed 1 electron. So it is very important to check where to subtract those electrons, because we can subtract them anywhere, but we have to follow a certain guideline. Now we know that these numbers, they represent the energy levels. N is equals to 1, N is equals to 2, N is equals to 3, N is equals to 4. Reviewing the basics just quickly, we know that when we draw, let's say, an atomic structure of oxygen, well, let us draw for the very same element, which is sodium. We know that we are going to have energy levels. Some say it's energy shells. Then since it's element number 11, it simply means that it will have 11 electrons. Remember this configuration, 2882. So we have 2 electrons on the first energy level. This is the third energy level. I mean the second energy level. I'm sorry, this should be the first. I've written 2 instead of 1. Then this will be the second energy level. This will be the third energy level. So this n is equals to 1, n is equals to 2. It's those 1s2, these numbers, 2s2. It simply means that this is the second energy level. 2p6, second energy level, but it's p orbital. 3s1, the third energy level. So here, when we continue this, we're going to have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So this simply means that on the third energy level, we have one electron. There it is. This one is the very same one that you see here. And then on the second energy level, we have 8 electrons, which 6 of them, they are from p orbital. As you can see, p, is 2p6, but 2 means energy level. 2 means the very same second energy level, but we have 2 s orbital, we have 6 p orbital. So you can see the sum of 2 and 6 will give you 8. Then on the first energy level, it simply tells you that we have 2 electrons, which are these electrons that you see here. I hope you can see what is happening here. Now going back to our electron configuration of ions, you should listen to this. Where do we remove the electrons in order to get electron configuration of an ion? We remove on the highest energy level. So the highest energy level, you can see it's the 3. So it simply means that we are going to remove our 1 electron here. This is the highest energy level. And then the electron configuration of this will be 1s2, 2s2, 2p6. This is the electron configuration of our ion. Remember, I said we are going to relate or integrate this concept with isoelectronic. Isoelectronic are those substances with equal number of electrons. Different species with equal number of electrons. Let us look at our periodic table. While we are still busy with sodium ion, this is our sodium. But remember that we have removed 1 electron. Removing 1 electron, we get here. Remember that it goes this direction. From here, we start here. From here, we start here. So after removing 1 electron, it takes us back to element number 10. As you can see, neon, it's element number 10. It has 10 protons, 10 electrons. Sodium ion, actually the original sodium, the neutral one, it has 11 protons, 11 electrons. So if we have a charge, it means that we are running short of 1 electron. So it simply means that we have 11 protons and 10 electrons. You can see that these electrons are the same as neon. So sodium ion and neon, they are isoelectronic to each other. We can further integrate this concept with noble gas. So let's say we want to write down the noble gas of this ion. Let's go back to the electron configuration. Looking at this, we can check a noble gas that consists of any piece or any part of this electron configuration. And by looking at the periodic table, we can easily tell, because we know very well that our sodium is no longer here, it's actually here. Then it means the previous noble gas will be helium. So looking at helium is simply 1s2. That is the electron configuration of helium. So you can see that part, it's actually here. So where we see that part, we can simply put our helium. Then the remaining, we put it back. Now that we know the electron configuration of sodium ion and sodium, and also looked at the Nobel core notation, also looked at the isoelectronic. Let us go ahead and find the electron configuration of oxygen ion. We said oxygen has 1s2, 2s2, 2p, 2p4. So in this case, we want oxygen 2 minus. This simply means that we've added electron. I hope you can see, since we have a negative charge. It means that we have efficient number of electrons. So where are we going to add? We cannot add here, surely, because we know that the s orbital can only accommodate to a maximum of 2 electrons. So we have this p orbital that has 4 electrons. Simply means that we are going to add our 2 electrons here. So we're going to have 1s2, 2s2, and then here we're going to have 2p6. And then we can also determine the isoelectronic. You will see that it will be, because when you add 2 electrons, it means you are going this direction. Instead of 8 electrons, we have 10 electrons, because here we have 8 protons and 10 electrons. In that case, the element that has 10 electrons is neon. Let us look at more challenging ions. Suppose we have ion 3 plus. Now looking at the electron configuration of ion, we are going to have, I hope you've written down that template. We know that ion is element number 26. So we have 1s2, 2s2, 2p6. We have 10 now. 3s2, 3p6. We have 18 now. 4s2. We have 20 now. 3d6. Now in this case, we need to integrate everything we've learned from quantum numbers to electron configuration. Remember that we have 3 plus. It means that we are going to remove 3 electrons. 3 electrons should be removed from our electron configuration. Now the question is, are we going to remove here, 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 or here? Remember that we remove from the highest energy level. So in this case, you can see that this is the highest energy level. We are going to remove 2 of these, but I want you to check something from here. Since we can see that this is the only energy level number 4 that we have, so we know that 2 of these electrons will be removed from here. Now we must remove an extra 1 electron, because remember that we need to remove 3 electrons. The question is, are we going to remove from D, P, or S? Because we know that this is totally out, and then where are we going to remove that 1 electron? because you can see that the energy levels are the same but different orbitals. Now in this case, we have to bring in the concept of angular momentum from quantum numbers, the subshell. Now we know very well that for S, our angular momentum is 0. For P, our angular momentum is 1. For D, our angular momentum is equals to 2. For F, our angular momentum is equals to 3. Remember the procedure. We start with the highest value of n, the highest n. The highest n, we are going to remove our electrons there. But in this case, we have same level of energy level. So where do we move? From s orbital, p orbital, or d orbital? It all relies on this. We are going to remove from the orbital that has the highest L, angular momentum. So in this case, you can see that S is the lowest angular momentum. P, well, it's not the highest. And then we have D. We don't have F, so it means the highest is this. Then it simply means that we are going to remove from here. This concept is applicable to when you have electron configuration that has the same energy level but different orbitals. Because you can see that when we remove electrons, we don't just look at the last part of the electron configuration. We have to follow a certain procedure. So the first thing that you have to check is the highest energy level. The second thing you have to check, if you have the same energy level, is the angular momentum. So if maybe we didn't have any d orbital, it means that we are going to remove from p orbital. If we didn't have d and p, then definitely sure we are going to remove from this one, because it would be the only highest energy level. So the electron configuration will be 1s2, 2s2, 2p6, 3s2, 3p6. We no longer have this, so it will be 3d5. Let us look at the last example that will make us use this principle again. Let's look at the electron configuration of indium ion. Let us start with indium quickly. We are going to have, by the way, indium is element number 49. Then let us go ahead and write the electron configuration. We have 1s2, 2s2, 2p6. We have 10 now. 3s2, 3p6, 4s2, 3d, 10. We have 30 now. And then from 3d10 we go to 4p, 6 is 36. Then from 4p we have 5s2, 4d10. I'm running out of space here, I'll just come here. And then 4d10 we have 5p1. Just to verify the number of electrons. Yes, it is 49. So in this case, we want to remove one electron. So the question is, where are we going to remove that electron? Because we can see that we have 5p as the highest, we have 5s2, we have 2 electrons, two orbitals from the same energy level. So the principle, the angular momentum will tell us. For s orbital, we said L is equals to 0. For p orbital, L is equals to 1. So we don't have a choice but to remove it here. So we can write everything and then without this part. And looking at the electron configuration, I'm using the Nobel core. We are going to have krypton. You can verify 5s2 and 4d10. So if you can check the electron configuration, this one up to here, it's for krypton. And then this is the last part that we have here, which is this. There will be lesson 1 or 2 of the very same concept, whereby we look at more questions. This was just an introduction. That's it for this lesson video. This is Wahula SJ. Thank you very much.